Okay. I know it's a lot of Christmas goodies. Okay. I've been trying to figure out how to get my mind around s- how to get my mind around um, linear algebra. Um, and I'm kind of struggling a little bit with it. It's kind of something, just re to learn something new at my age. It can be difficult sometimes. Um, but I guess there are folks who will try and tell themselves that they've discovered something new and incredible about a given that they've discovered something new and incredible about a given field of science. And all I've got to say really is, you know, folks need to realize that first of all, AI's dumb. Okay, it tries to pass it off as smart, but really it's whatever gets swept up in its training data into the you know and if you're a smart person, you might be able to talk it into saying into actually finding real fact, but there's no guarantees. It's one of the reasons why I don't particularly rely on AI in order to do research. Uh, in no small part because it, I don't want something, I don't want a source that's going to mislead me on the basics starting out. As tempting as it is, as much as we want a sort of a kind of free backup brain. It's it, here's the thing about my approach. I want to at least have some degree of portability of what I know. Okay, I want to be able to carry it with me beyond the computer. The more I can just bring it up from off the top of my head, the better. You know, up until this point, I've spent a lot of time re reviewing and refreshing my memory on algebra and basic algebra and trying to get underneath the hood of those principles so that I can so that I can more fluidly think about the more advanced stuff. I want to be able to understand the basics well enough that I can build that I can be fluent when I'm thinking about the more advanced stuff. I don't want to simply understand it by rote because rote is that's difficult to kind of, remember, to retain. I prefer to learn things as systems. That means I often have to trust what scientists and mathematicians and other experts say. But here's the thing about it. Here's the thing about the way a lot of the people who are challenging them as experts, what keeps striking me. And what keeps striking me is that they're often bizarrely inconsistent in the way they construct things. Because they're thinking, I know best, I understand best, I am the new Galileo. Thing about Galileo though is that Galileo started from evidence and reasoned upwards. He didn't he didn't take an approach where he was just going, "Oh, I just want to be new and daring and different," or "Oh, I want to dress up my sort of ancient, you know, Bronze Age sort of information out of the Bible, dress that up as being cutting edge science." I encounter things a lot when I'm arguing with people, the flat earthers. I encounter the same arguments over and over again. Um, I want to kind of note something. Okay. Yeah, this is gonna be a kind of a brief sort of. Okay, I'm just gonna use the back page here, and I want you to be able to see this. I'm going to draw as close as I can get to a circle freehand. I'm not a very good drawer, um, sketcher, but I think you'll get the point um, of what I'm trying to get across. All right. So what I'm drawing right now is a circle with concentric circles within it, and you're just gonna have to imagine the that this is all nice and straight. So, according to a lot of flat earthers, this is about how lines of latitude work. You've got this concentric circles. So, when you go west, supposedly you're going to be following these circles around the world. And they need to do this because if they try to use the side on sort of maps, with with North America, South America, Europe, Asia, Africa, and so on and so forth. If they tried to do that, they would have to answer one rather inconvenient question. And that inconvenient question is, how the heck do people in the Pacific Ocean get back around to the northern western hemisphere? And the answer, of course, for them is that everything goes in a circle around the North Pole. And that's what I'm representing here. These, as we go along, are lines of latitude, are circles of latitude. Now, to be fair, in reality, they are circles. They look like lines when we're looking at them from, you know, looking towards the planet Earth, with in that north south sort of sensibility. But here's the thing. And it's a very important thing, and I'm gonna kind of draw some lines to get you to understand what I'm getting at. Now you're gonna realize something when I do this. Now, you see that each circle, and I kind of missed this particular circle, but still, just imagine it. Just imagine it hits. What I'm drawing here, these are basically meant to be tangent lines to the circles. So if you've got a circle, you can always draw a line that crosses that circle at you know at that one point and then goes on forever. So it comes in from God knows where, hits the circle at one point, and then goes on forever. So it's not going across the circle in any way, not creating an arc or of any sort of size or shape, but it then goes on forever. Now, if we're doing a Euclidean plane, then if I should be able to go up, to the right, to the left, and down, and wherever I go, I'm just going to keep going until I reach the edge of the figure, right? Or if this is an infinite plane, you notice how that works? That's a Euclidean plane, and that's Euclidean movement. You go in a straight line, and you keep going until you hit the boundary, or you just keep on going. But the important thing is that you're always going to be traveling in a straight line. If you don't deviate from from the orientation you've picked, northwest, south, or whatever. If it's a flat surface, you're just going to keep on going. You're just going to keep on going until, I guess, you hit the edge. And the the same is true if you're talking about a Euclidean a figure in the Euclidean plane, the flat plane, that if you're talking about a circle or a disc in that plane. And you're going to notice what these lines do. If these circles are the lines of latitude, if they are the parallels, if these circles go on, um, are simply laid flat, and we travel around them in order to travel around the world, if that's the way this works, then we have a problem here. And I think you'll notice, look at this one in particular. We start near the North Pole, right here, this dot right here. We start near the North Pole, and then we go a line of latitude further south and further south and further south. and further south and further south. What's happening here? I mean, this should be westward if, if we're judging by the direction on the camera. If we're going west here, we should just be going straight west. After all, this is supposed to be a Euclidean flat map, but they're not thinking too hard about what they've constructed. If these are circles and the geometry is Euclidean, then you just keep on going in a straight line. You can't do anything but do that. If you're somehow magically being guided around in a circle, then it's not Euclidean. That is a curved geometry. If you're going around in circles, if you can't help but go around in circles, if you set out towards the west, going in this direction, and let me kind of let's see. Just want to make sure what. Okay, so it's on this side. Okay, so if we're going off in this direction to the west, right? If we're going off in this direction, they want you to believe that what's going to happen is that you're going to, and maybe that's east from it, but let's just, whatever direction we're talking about here, they want you to believe that what's going on is it follows the arrow right here. Yeah. They want you to believe that it's going to follow that arrow and go around and around and around and around. But why would it do that? If you're talking a Euclidean flat plane, the basic idea is the shortest distance between 2 points is a straight line. And if you set your feet to the ground to go, you keep on going in that straight line because there's nothing to curve you. There's nothing to draw your path, to deflect your path otherwise. And the irony is, given the geometry, given a Euclidean geometry, you are basically, if you look at this as if we were looking at a map of, if you're looking at this as if we're looking at the map, in the north south sort of configuration, in that sort of flat, sort of North America, South America, you know, Europe, Asia, Africa sort of configuration. If you're doing that, then what's going to happen is that as you go west, in the appearance of the map, in the appearance of the front map, where the Mercator projection and those like it, where the continents are all presented in a nice band, you look at it from that projection, and what you're going to see is a line. You're going to see a curve, and the curve is going to gradually deflect towards the southern ice wall that they posit exists. Now, putting aside just how poorly this all fits together, putting aside, you know, the problems with this whole thing being about 70, 60, 70,000 miles, because you have to be wider than the equator. That's another thing. That's another consequence of Euclidean geometry. Is that the longer the radius, the greater the perimeter, and also the greater the area. But it's the perimeter that matters. In terms of how you get to 60 to 70,000 miles, which is easily 2 to 3 times the 2 to 3 times the equatorial width of the world. I mean, that's about 24,000 miles or so. So, as you can see, it's falling apart in some pretty peculiar ways. And as we would see a curve go down towards different lines of latitude, you'd see a curve, a deflection from our perspective from going west to going south. But we don't see that. If I go west, if I set my feet to the west and do that right like that, guess what? I keep going west. And if I go west far enough, I come back to the point where I started. And that is the true circle. That is the real circle that exists on our globe. That's the value of a closed, curved geometry, is that you can have things come back to where they started. And that's the thing. We can curve that path around because we're not asking um, we're not asking the geometry to do something it can't. A curved geometry can turn you around, can get you to where you are, returning to the spot you started from. And in the process, still have you taking that what seems like a straight path to you. What seems like you taking steps and going little by little back to where you came from. Of course, you this sort of this curvature actually helps there to be straight line travel in the world. Because whichever sort of direction you go, you're not being deflected away from that. You go north, you go north. You go south, you go south. You go west, you go west. You go east, you go east. And that is the one of the beauties of using a globe. The directions all work, and you don't have to kind of posit that there's some sort of force that's going to curve your path around, because there is something doing that, but it's doing it in another dimension. It's doing it in a third dimension. So rather than end up apparently, instead of kind of ironically sending you on a deflected path, a deflected curved path, it keeps you going. So this is the value of understanding where you're starting from. Um, but because there are a lot of things, that I kind of researched trying to counter people, and it led me to understand things in a much more intuitive manner. Um, like inertia. Okay, why does a helicopter remain, spinning above a place and not just get knocked off, going 1,000 miles an hour this way or whatever way? Why is it not doing that? Well, because of inertia. Movement of my hand moves the pen. I don't have to keep on nudging it. I don't have to keep on nudging it. I can throw it to my other hand because of inertia, because I've imparted a force, and that force will keep on going for as long as it's not opposed by some other force. And what's stopping it? Hitting my other hand, and then getting then. Of course, I could just bounce it off my other hand. Or that's an example of torque right there, where it just goes over twisting. But the point is, Newton's laws work. Newton's laws work. So I toss something, it keeps going until it, an object in motion stays in motion until an unbalanced force changes its motion. And so if you're spinning around on the earth, if you're riding the earth, held to it by gravitation, you will be going about 1,000 miles an hour at the equator. Thus, the further north you go or the further south, you'll be carried along there. And when you lift off your helicopter, if you lift off your helicopter, well, you are starting out on the ground. You're starting out on the ground. You were starting out, and you were going 1,000 miles an hour with the rest of the planet. You know, you were going 1,000 miles an hour with the rest of the planet, and when you lift up, you still are going 1,000 miles. You still are going 1,000 miles an hour, and so you know it will. You will keep on going that fast in that direction or that direction. You'll keep on going that fast until something changes your motion. Now, that could be your engine, you engaging the rotors in the engine to go this way or that. Or it could be that some hideous blast wave comes in from the side and knocks you over. But, you know, you'd have to basically, in order to catch up with the rotation of the Earth, you would have to be given enough, be, pushed, accelerated with enough force to get you going 1,000 miles an hour in that, or to push against that to get to zero in relation to the turning of the planet, or to get ahead of that, you would have to add you would have to add some kind of force and acceleration. So the reason why a helicopter can lift up and just hover there and not, have the earth kind of going underneath it is that really you start out spinning with the earth, you start out going around and around and around. You're not going to just suddenly stop when you lift into the air. You're going to keep on going. You're going to keep on going with what you were resting upon in to begin with. You're going to keep on going if you lift off. Now you might deflect if you start going, north or south of the equator. You might start drifting, but that's going to be because you're still going to be carrying that speed. So if you're going 1,000 miles an hour at the equator, and then you go up to where it's more like 800 miles an hour, well, you might just get 200 miles an hour ahead of yourself, and that's going to deflect your direction. You see how that works? That's the key thing right there. They're not really get using an integrated perspective. When I talked about beginner's mind, part of the use of a beginner's mind is it helps you to kind of say, okay, what are all the pieces of this subject I want to know about? What are all the little things that fit together to create the subject that I'm trying to learn? And by learning those more thoroughly, you can understand better how the system operates. Yeah, I think that's what a lot of people fail to do. That they want everything to work, according to what's in their heads. They don't want to have to do any extra effort. They just want to, keep on going with the way they were thinking before, with the understanding they had before. And really that's what so often makes them so desperately wrong is that they simply do not think things through. When you get into a system where everything is more political as to the reasons why, or social or cultural, you know the reasons as to why you believe a thing, when you get into that sort of situation, you're kind of dooming yourself to a certain kind of misunderstanding of the subject or an incomplete, you know, frictionful sort of, twisted sort of understanding. You want to start out from the assumption that you don't know what you're dealing with, and then you work up and you kind of get the bits and pieces together and figure those out. Okay, so all that explained. Yeah, I'm getting a little tired here. I don't want to get to the point where I'm just like, getting to nod off. No. So what I'm gonna do here, what am I gonna do here? I'm gonna tell you. I'm gonna give you an advice, and this is from somebody who regularly aced tests without having to cram for them. Learn the system of a thing. People might call you a sheep or whatever, but a lot of those people. Here's the thing I would point out: if you are not able to understand things for yourself, then the default behavior of most people that I've observed, the default behavior is to follow convention, to follow whatever convention that they're used to. If it's Christian, they're going to follow Christian conventions. If they're atheists or crunchy or whatever, they're going to follow the conventions that they understand about the world. And that might work for them, but it doesn't really translate well to other people or to actual good scientific principles. So, the long and the short of it, and I think I'm going to leave it here, is that, well, for one thing, don't don't be so eager to fit everything in to everything you already know. Often it's a good idea to unlearn what you have learned. Because the extraordinary thing that happens when you learn things, when you develop an understanding of things, you kind of get a better idea. You can things become transparent. Things become more, you know, you become able to analyze things on a more factual basis. And that's the important thing there. Because politics and other things, they're interpreters of fact. It's like what Cypher says in the Matrix to image construct the image constructors work for the system. If you want to see things for yourself, understand things for yourself, you have to you have to kind of dig into the basics of the subject and build up from there so that you're able to say, okay, here are the facts. This is how you get from those facts to this conclusion. That's logic. That's reason. You start from the beginning. So, also don't learn things just for the sake of argument, just for the sake of arguing things. Learn things for their own sake. And that way you can get a thorough understanding. And once you have that thorough understanding, you can use that thorough understanding to fact check, to determine whether what somebody is saying to you is right or wrong based on the facts you know. And that's the thing. That's the important thing right there. Being able to see through the facts to the truth. It's not a cultural thing, it's not a political thing. This is a matter of how you build your particular understanding of things. So, yeah, I'm beginning to kind of get a little tired, so I'm going to sign out here. So, have a good night.